squared plus x plus 2. And you and I are going to find the limit. That's a that's a function, but it's not a rational function. You and I are going to find the limit as x goes to infinity of this. And then we're going to find the limit as x goes to infinity, except, I'm sorry, negative infinity of the same expression. Believe it or not, Evan, I always like to start out with doing those little short, fast ways to do it. That's how I'm going to start this. Okay? Now, some ideas. If you got something like this, you're doing a test, and you never saw this approach prior, I mean, couldn't you really put this into a calculator graph and see what's going on? You surely could. Investigate it. Let me just see what goes on with this graph. So that's something we might consider. I might pop it up there in the end. But I guess it's not a rational function because it has a radical, true? But we can still approach it the same way. Like, what's the highest power up here? X to the first. If you think about these as separate, the highest power in the denominator is right there, x squared, but it's got a what? Square root. So, and Joe, you told me earlier, square root of x squared was just a what? Just x, right? So think about it, when you've got a 2x with a what? An x. The only thing we got to be careful of is this. Because it was the square root of x squared, which is technically a what?
Plus minus.
Yeah, a plus or minus x. So, what we're saying here, everyone, if you're going towards positive infinity, which one of these two would it be? That piece or that piece in the top one? If you're going towards positive infinity.
X.
Yeah, so I can actually think of this as an x. But what about this one as you go towards negative infinity? Then you're going to have to think of that as the what?
Negative x.
Negative x. Now we're going to be able to get these answers in a very short, easy way like before. I'm looking at this. See all this right here? I'm thinking of that as, aha! That's like a 2x over a positive x, which is just a what? So guess where the horace is. This thing has a horizontal asymptote. There's a horizontal asymptote at y equal to 2. Guess what the limit is? That's the horizontal. It does. It's a funny looking graph. That's why I was going to fill out the graph in calculus. We'll see how nice it comes out in the calculator. This graph has a horizontal asymptote at y equal to 2. So what's the limit going to be? It's like, I'll just do this. It is just going to approach that 2. You betcha. You betcha. You really? I didn't have to make the graph. I know that because of this portion right here. I took up the highest piece.
What if it was 2x squared and x?
2x squared over x. Any radicals in there? Oh, then you're back to the rational functions. Do you agree? If you just had this, but you don't have any square roots, then you can think of this as higher power on the top. Think of the end behavior, it's going that way. That's going towards infinity. Do you agree? Even if you had this here. Look, now you got a rational function. Do you agree? Look, end behavior. 2x over x. What's the end behavior? That thing's simplified. It's going to infinity. The limit as this goes towards infinity. Hey, and when this thing has a positive, but what about this right here? There it is. But this is going towards what?
Negative.
And now look, we're coming back to this definition. We know that the absolute value of x is actually 2 pieces. And when x is less than 0, it turns into what? Negative x. So how am I going to think of this part now? Because of this.
2x over negative x.
There you go. Good job. This is my, what I'm going to call it, my horace. It really does. This is the horizontal asymptote right here. There's a horizontal asymptote of this function, this funny looking function with the radicals at y equal to 2x over negative x. This had a horizontal asymptote at y equal to 2. I'm going to write it this way. 2x over positive x, which is 2. This is just a negative what? So what's this answer? Without any graph, without any algebraic work, this has to be 2. What's this answer? Cool. Now I think we should take a second and definitely check it. If you want to go and do it that way I did before, go right ahead. What do you think you would divide everywhere? I would divide x squareds, because even though it was in a radical, what was the highest power?
Okay.
I would divide x, 1 over x squared, good. 1 over x squared there and 1 over x squared there. But then you gotta insert your 1 over x squared inside the that radical and stuff like that. Alright. Hey, when I'm gonna hit the light here. Let's look at this thing. What was the equation? How nice is this? Is it nice? Oh, I gotta turn my plot off. Zoom 6, right? For a nice window. And y equals, what did it have? 2x divided by square root x squared plus x plus 2. How good is it? Oh yeah. And when you want to use trace, I'm going to trace this baby. Watch the y value. Just watch. Where's it going? I can zoom this better too. We really want to see these numbers a little bit better. That looks better. I'm just keep hitting trace, okay? Go, right arrow. Where does it look like that's going?
Closer to 2.
It's getting closer and closer and closer and closer. There's a horizontal asymptote right there. What about over here though? What's going on when you go towards negative infinity? It's going towards what? Negative 2. Cool. So that's what that graph is. So this is a great tool just to investigate things like this. Like, are you sure? That looks complicated. You should pull this out and look at it. So please feel free to do that. Please feel free to do that. Isn't that cool? Right. Yeah. Hey, well, let me look at the craziest one out of this section. I want to look in front of the radical. Will you try it? This is number 24. The page 141. Find a limit as x approaches negative infinity of the square root of 9x to the 6 minus x all over x cubed plus 1. This is going towards what? Negative infinity. So when I watch, everyone see that square root? Don't forget it. This, right? Okay, let's see the behavior of all that. Is that a square root of 9x to the 6? What would that be?
Wouldn't that just be 9 x?
Square root of 9 is 3, right?
Yeah.
Good. And then what's the square root of x to the 6?
X to the 3rd.
Third.
X to the 3rd. But is it positive or is it negative? Because it's going towards negative infinity. And it's x cubed, isn't it? Hey, what'd you put? X squared?
I kept the 9. I didn't take the. I thought it was going to be the 6 with a.
Oh, I gotcha.
3.
So that's the top thing right there, right, everyone? Why did I make it negative though? Go there. Now what's this bottom half right there? This should be our HA. This graph has a horizontal asymptote at y equal to negative 3x cubed over x cubed. Do you know the answer? Without even making a graph, y equals negative 3. The limit? Negative 3. You need that? Because it was going towards negative 3. Hey, that seems like the craziest one. They have one with e the x's and e the negative x's. You just gotta have knowledge of those graphs. E the x exponentially grows, e to a negative x exponentially decreases and goes towards 0. Cool. I'm sure you'll get 15th grade practice, 17th grade practice. 19, it had a square root in it, but it still didn't have the highest power. The highest power of t squareds. Cool. Hey, please keep in mind, I even would spend more and more time on this section. I would. But there are other great techniques to go in limits to infinity. Has anybody had calculus before? Oh, there's always one. All right. Do you remember L'Hopital's rule? L'Hopital's rule?
I remember.
Okay, L'Hopital. Right, L'Hopital's rule deals with limits to infinity. It's a very, very, very elegant way to find limits. We just gotta learn about derivatives first. So I can't teach it now because we don't know derivatives. But once you get derivatives down, there's another way to what? Deal with these. And what I find, this is what my point is, I look on final exams, what techniques students do, and I see students use that more often than this stuff. You know, it's good to know about horizontal aspects. When it gets a little more complicated, they're using like, maybe perhaps L'Hopital rule or something like that. Keep in mind, hey, to summary this, what's the 3 ways you can find limits? You can do it what? Graphically? What's the other way you can find a limit? You can do it numerically. You just plug numbers really close to it. If it's going towards infinity, you put very, very large negative numbers. Very, very large if it's going toward positive. And then the last way is get these two-sided limits, and we're just doing it algebraically. And this problem algebraically would be multiplying like whatever x to the 6, whatever x to the 6. Cool. Alright, good deal. Alright, oh cool, we get to define a derivative. Derivative of a function. Alright, what is the derivative of a function? We won't need this anymore then. We don't need any of this, that was just for limits. Alright, derivative of a function. Derivative of a function. Let's define it. Here's a point. Here's a point. And there's our function f of x. Let's label this as x. If I call that x, anybody know what I can call the y value at x? F of x. Will that work? Yeah, okay. Alright, cool. So far so good, I'll get this out of the way. We're going to define a derivative. Now, we're going to use that letter h. I saw h in that last section. So when I do a distance from this point to this point, horizontally, I'm going to call this h. From there to there, this horizontal distance, from this location to that location where that is, that horizontal distance I'm going to call h. H for horizontal. All right. So, I want to see my dot right there? What do you think I can call that value then? That'll work. X plus x is the distance from there to there. The distance from here to here is h, so I can call this x plus h. Sound good? Remember, we're doing this as proof, so we're going to actually derive this, come up with some expression for the actual derivative. So that's x plus h. Now, I said, what's the y value at this x value? We called it f of x. What do you think you call the y value at that x? F of whatever that is, right? What's the y value here? F of x plus h. That's what I call it. Alright, so that's f of x plus h, that's f of x. Now I'm going to start out, before we do a derivative or a rate of change, let's just go back to college algebra. Not pre-algebra, college algebra, algebra 2, that kind of stuff. And if I took a straight line from here to here, that's called a secant. So I just want to let everyone know this is called a secant. It's a segment that actually went and intersected this curve in 2 places. Cut through the curve, it's called a secant. What's the math formula? Just go back to algebra days. What's the algebra formula for slope of a secant? We need to start there before we get the formula for the derivative. Because it deals with slope. What's the slope of that secant? Y sub 2 minus what? Y sub 2 minus y sub 1 over x sub 2 minus x sub 1. True? Alright, but help me out. What's this y sub 2? What's this y sub 1? What's this x sub 2? What's that x sub 1? Maybe we should write them as xy coordinates. That point right there, everyone, is the point x plus h, comma, x. What's this point? That point right there is the point x, comma, f of x. Right, everyone? So what would this come out to be? That's x, comma, f of x. That's x plus h, comma, whoops, what's this? I apologize. This is f of what?
X.
saw the eyes. I'm like, what'd you write up there? X plus h comma f of x plus h, x comma f of x. All right, let's jam it all in here. And when y sub 2 minus y sub 1, okay, slope is secant, y sub 2 minus y sub 1, f of x plus h minus f of x. Now how about the x's? X plus h minus x. This is the math formula for slope of any secant. If we're dealing with this funny little h in there. Now, can I simplify anything in there? What does that come out to be? Remember, this is just the theory. If you hate theory, you can ignore all this and wait for the formula. This is kind of fun. What simplifies in the denominator though?
It's h.
Yeah, it's just h. So, and this is actually the formula, I guess. In terms of any function where I reference as h the distance from this point to the next point, in terms of a horizontal distance. That's slope of a what? Secant. I want to tell you what we're trying to do in section 2.7. You and I are trying to come up with a formula for the slope of a tangent. Alright? This is slope of a what? Secant. You and I got to figure out a elegant math formula with math notation that represents not that slope, but what color is this? Pink or red? I'm not good with colors.
Kind of a salmon.
Okay, thank you. We're looking for this slope. Right there. We need a formula for that. We need a formula for that slope. We know the formula for this secant, right? So here's an idea. How about we just draw another secant, but we'll bring it closer. Remember when we kept getting closer and closer and closer? So Erwin, this is what I'm going to do. You ready? I'm just going to keep erasing. I got it easy because I'm going to keep erasing. But remember, we're just doing a theory here. So there's slope of secant. True. I'm going to move this dot now. I'm going to